In this example, we are going to find the points on this hyperbolic cylinder, x squared minus z squared minus 1 equals 0, pictured here, or x squared minus z squared equals 1. We want to find the points which are closest to the origin. And very clearly we can see that both of these points lie on the x-axis. They occur when x is equal to +1 or -1. As we discussed in the previous video, we talked about finding the distance from any point to the origin. So that point to 0, 0, 0 is always going to look like this when we put those or that distance into the distance formula. And to simplify our calculations for our distance function that we want to minimize, we're going to use x squared plus y squared plus z squared. We're going to disregard the negative. If we minimize this function, then we will be minimizing the square root function. So ideally, we want to minimize this function, but we need to determine a point on the given cylinder. So the cylinder is our constraint, and I'm going to write this as this function g. G of x, y, z equals x squared minus z squared minus 1. Now, we haven't discussed Lagrange multipliers at all yet. I've mentioned them, but I'm going to show you an example before we formally define them. So what the method says is that we are going to find these coordinates, x, y, z, in conjunction with the value or values, you can have more than one, constant, lambda. So this guy right here is lambda. And we need to find them such that g, my constraint, is equal to 0. So here I've got my function in terms of being equal to 0. So if I had that constant on the other side of the equation, we need to move it over. And what we're going to do is we're going to say the gradient of f equals lambda times the gradient of g. Now when I scroll to find my gradient of f here on the screen, I'm going to run out of space, but we can see partial with respect to x would be 2x, partial with respect to y of this function is 2y, and then the partial with respect to z will be 2z. So my gradient of f is 2xi plus 2yj plus 2zk. And the gradient of g, that is going to give me 2xi, there's no y term, so I'd have plus 0j minus 2zk. All right, so we want to solve this system of equations for lambda. Considering that property listed, I can say 2xi plus 2yj plus 2zk is going to equal lambda times gradient of g, 2xi minus 2zk. So if I take this lambda and distribute, I would have 2 lambda x minus 2 lambda z for my I and k terms respectively. So at this point, we can match up these coefficients to create a system of equations. And I'm going to end up with 2x equals 2 lambda x, 2y equals 0, and 2z. So positive 2z equals negative 2 lambda z. So to give myself some more space, I'm going to skip to the next page and rewrite this. So again, we need to solve for lambda, and we're going to solve this system for lambda subject to our constraint. Well, it's pretty easy for us to notice right away that y is going to be equal to 0, right? So that's one of the things that we notice. We also notice that I can't let x be 0. if I let x be 0, then I would end up with -1 equals z squared, zeroing this term out and moving that to the other side. And square of a number can't be equal to a -1. So we notice that, and then also x cannot equal 0. If we consider this first equation, it's fairly easy for us to determine that lambda would be equal to 1. 2x equals 2 lambda x. Divide on both sides by 2x. I've got 1 equals lambda. And if I let that lambda equal 1 and I plug it in to my third equation, that gives me 2z minus or equals -2 times 1z. 2z equals -2z. The only way we can make this work is if z is also equal to 0. So what we have determined, thinking about this system, is that y is 0, z is 0, x cannot be equal to 0. So therefore, the points on the cylinder closest to the origin must be in the form of x, 0, 0. Well, what could x be? Let's use our constraint. Recall, x squared minus z squared minus 1 is 0. X minus 0 squared minus 1 equals 0. That's going to give me that x squared equals 1, or rather x equals plus or minus 1. So my options for the solution would be +1, 0, 0, or -1, 0, 0. Both of these are 1 unit away from the origin, which is what we noticed in that original picture. These are my 2 points closest to the origin. So this is a significantly shorter process, this Lagrange multiplier process, than actually doing that optimization problem, the 2 methods, or the 1 method that we used in the previous 2 videos to this. All right, so in the next video, I'm going to define the method of Lagrange multipliers, and that's what we'll use now to optimize systems with constraints. As always, email me if you have any questions.